Okay, so yes, thank you to the organizer for giving me the opportunity to present this work. So I'm going to talk about tractor geometry of null-infinity. So indeed, during the last week, we've heard about asymptotic symmetries. We had Mark giving us a lecture. I tried to introduce you to BMS symmetries last Friday. We heard about tractors. We had this lecture on Cartan geometry by Andreas. Ambient space, Michael Eastwood gave us this talk. And the aim of this presentation is to show that, in fact, these are very closely related subjects. And you perhaps might already have a glimpse of why this is the case after listening to Rod Gover's lecture this week. He told us about boundary calculus. He explained that this whole tractor formalism is a very nice one to study conformally compact manifold in an invariant way. But in this lecture, I'm going to make this relationship fully precise. Other motivation for this work are recent development in gravity-S matrix. So it was understood in the last years that in fact the BMS group is a symmetry group for the gravity-S matrix, while identities are then seen to be Weinberg's theorem. So it gave a new derivation of this Weinberg's theorem, and in the classical side of it, it was gravity memory effect where we understood in relation with this, as being transition between gravity vector and in relation with the action of the BMS group. And perhaps last but not least, there was this realization that by Hawking, Strominger, and Perry, that Hawking initial derivation, in fact, it implicitly relied on the implicit assumption of uniqueness of gravity vector. In this sense, the initial derivation does not hold. Then there was a lot of question about whether or not this allows to go to solve the information paradox. Okay, so I'm going to take this as motivation for why you should care about this gravity vector and try to make sense of them in an as deep way as you can, in the sense that in a fully geometrical way. Okay. So I'm going to discuss asymptotic symmetries, and accordingly, I'm going to concentrate on examples where you have asymptotic symmetries, so asymptotically ADS3, and also all asymptotically flat spacetime in 8 dimension bigger than 3, because 2 dimension is too degenerate for what I want to do. So the first part of this talk, in fact, I could have presented the whole talk as just going through Rod Gover's lecture, especially the second one, and trying to spot how things get different in these very specific cases. And you would see that indeed there are differences, and that could be an exercise, but I'm not going to do it this way because it would be a bit tedious just to redo the same lecture. So presentation will be different, but in spirit, this is what you could do. So also I should say that for the asymptotically flat case, there are closely related discussion in the very early twister works, especially in this 1973 paper, Penrose-McCallum paper, which is one of the very first twister paper, where there is something called asymptotic local twisters, which is something which has been somewhat forgotten in the literature, but which is very closely related to what I'm going to discuss. There's also a twister newsletter and written notes by Lionel Mason from 1986, which has some relationship to what I'm going to talk about. So in some sense, you might argue actually that local twisters, they predate tractors. So in some sense, you could say that everything was already contained here. But I think it's fair to say that now things are much more mature. And I think Rod Gover's lecture showed that indeed you can do much more by doing, the tractor formalism is much more mature in this sense. Okay, but anyway, okay, you might argue that what I'm going to say in the first part of this talk, in some sense, if you know by heart all this literature, in some sense is already hidden there. But in the second part of the talk, I'm going to develop tractor calculus in a fully invariant way at null-infinity, so in an intrinsic way. And this is for sure, nobody would argue that these are not genuinely new results. Okay. Yeah, so about exactly the take-home message, I just want to say you this because then if you get asleep, at least you would, this is the picture you should remember, is that at the conform boundary of asymptotically flat spacetime and asymptotically ADS, there is always such thing that you can call a tractor bundle, which is canonical. So it's always there, even for at the boundary of flat spacetimes. And then the presence in the very specific case of asymptotically ADS3 and asymptotically flat case, the presence of asymptotic symmetries is directly related to the fact that your usual theorems, which are that you have a unique normal Cartan connection, is wrong. It's not, you do not have a unique Cartan connection. It's directly related to this asymptotic symmetry. So the usual fact in conformal geometry fail. And then, all statements about gravity vacua, they are just statements about the fact that flat connections like this, which are flat, are again not unique, which means very practically that you have many ways of identifying your manifold with a model. However, when you take such conformal geometry, but they are the boundary of some spacetimes, you do get a unique connection which is induced. And then in a very particular case of four-dimensional gravity, something interesting happens is that the curvature of this connection precisely encodes gravitational radiation. Okay, so that's, and by this I mean this coefficient in the Newman-Penrose formalism. Okay, so I'm flashing you this. I'm going to repeat this story many times, but I just want to have this very clear where I'm going at least once. Okay, so let me first review more elementary stuff about asymptotically flat spacetime and asymptotically ADS-free spacetimes. So here's the definition of an asymptotically simple spacetime. So you've been through this definition many times during the week, so I'm going to be quick. So again, your physical spacetime with tilde is asymptotically simple if there exists another spacetime without tildes, but now the spacetime M has a boundary. So the picture is that you add the boundary to your physical spacetime. And then there is a metric on this unphysical spacetime. It extends up to the boundary. Yes. Okay, so, well, so conformally compact seems to be saying that you want that M is compact, and it's a bit, well, I think what we, depends to which level of precision you want to do. I mean, for physicists, I think this is the same thing, yeah. But I mean, here you don't necessarily need, when you mean asymptotically simple, you don't necessarily mean that perhaps the spacetime is compact. Perhaps it's just, you have a bunch of boundaries and perhaps they don't glue, I don't know. You're sort of going around this trouble. Okay. So here, perhaps it's even just a local picture. You just that. So I mean, this is Penrose terminology, asymptotically simple, and indeed in the math literature is more. You find this conformally compact, but conformally compact is much cleaner in the Riemannian case where you do have just one boundary. In Lorentzian signature, it's a bit tricky because you have these points here which are slightly behaves. Okay, and then you have these boundary defining functions, which is nowhere zero in the bulk, so that if you take the ratio with your unphysical metric to get the physical one, it gets to zero at the boundary. So in this sense, it's a boundary defining function. And you are going to say it's asymptotically de Sitter flat AGS. If on top of this inside you have Einstein's equation, perhaps you might want to weaken this. You might want to ask for some follow-up, but I'm not going to need this here. But of course you can do that. And then the normal at the boundary has some constant sign, and the sign tells you about whether you're in the de Sitter case, flat or AGS. So lambda equals 0 is flat, positive is de Sitter, AGS is -1. Okay. So one thing I really want to emphasize is that, of course, there is nothing unique about this omega nor this g mu nu. They are not unique. Only the ratio is unique because the physical spacetime is unique. So really, because you can always rescale the metric, rescale omega, and you get the same physical metric. So really, what one is doing is working with this equivalence class of objects, and then you get this picture of compensator field. Anywhere in the bulk, you have this omega, which is, so if you're a mathematician, this is a weighted object. These are weighted objects, so not really metric, not really scalar field. So if this is a compensator field, you're introducing a new gauge symmetry, but you can always gauge, whenever omega is non-zero, you can gauge fix the symmetry by picking omega equal 1, and then you get the physical metric. Of course, here what you get, which is a bit more, is that if you go to the boundary, then omega is 0, and you cannot gauge fix this while rescaling, and you do have a genuine conform metric at the boundary. Okay, so indeed you have a conformal boundary, but you have slightly more. So you have this induced metric. What you do is you just take your conformal metric in the bulk. It's well defined everywhere by definition. You just restrict it at the boundary and get rescaled by some squared object. But you have something else. You have a weighted normal. So weighted normal, you take, well, just take your boundary defining function and you plug into it, take the derivative and you plug the inverse metric. You get a vector field and you just look at the way things rescale. And this weighted normal actually rescale by lambda -1. So it has weight -1. Of course, since the metric rescaled by lambda squared, the norm of the normal is a number, and this is this lambda. that differentiate the different situations. Okay. And then depending on what you care about, the type of situation you care about, you have different type of conformal geometry induced. So if lambda is 1, then the normal is time-like and the induced geometry is Riemannian. If lambda is -1, then the normal is space-like and the induced geometry is Lorentzian. And if the lambda is 0, the normal is null, which means that it's inside the boundary itself, and the induced geometry is something that goes under the name of Carrion or null or light-like. Really depends on the literature. And this is this thing that I already told you about on Friday. You have this normal, and the induced metric is degenerate. Okay. And so then you can sort of abstract this notion of Carrion geometry. That's already what I told you on Friday. And it goes back to Lévy-Leblond and Gibbons, Orbati and Duval sort of gave some advertising for this notion, which I think was interesting. So you want to call a Carrion manifold something where you have vector field, it's nowhere vanishing. You can go look for the integral line of this vector field. And what you're going to ask as a topological requirement that the total space now is a trivial bundle for these lines. And on the base, you have a manifold, and you want to ask that there is a metric on this space manifold. Okay, so there is a manifold on the quotients. So you should think it's some two sphere with a metric, and you have a line on top of it. In particular, what you can do is you can pull back the metric on the base, and you have a metric on the total space, which is degenerate, and the vector field is the degenerate direction. Okay, so that's, we want to call this a Carrion manifold. So at this stage, you might wonder, why should we give a name to such a thing? Because it's just, yes.
You get it for free, you don't need an HTML or you need
well, I mean, it depends how you, I mean, for me, here it's part of the definition if you want.
Sure.
But if you are the boundary of the infinity, acts as the equation.
So in that sense, yes.
Well, I mean, it's very natural. You see to ask that there is a metric on the quotient.
I know.
Because, yeah, from the space-time perspective, this is actually the equation. Okay, so again, why should you give a name to such a thing? Really, the reason why you care about these things is that they mirror Galilean geometry. So if you have a Lorentzian geometry, there is a sense in which you can take the speed of light going to infinity. You can make this precise. What it effectively does is that it opens up the null cone. The very limit, you get your space-time is foliated by degenerate null cone, and you have notion of absolute time. Each of these slides in absolute time. So the alternative to that is this Carrion limit, where you take the speed of light going to 0. That's the other picture. The cone shrinks into a line at the very limit. Your space-time is foliated by degenerate lines. Okay, so that's really the dual of the Galilean limit, and we had very nice talk by Stefan in the first week on homogeneous spaces that are this type and of this type. Yeah, and I just wanted to say that sometimes the literature, you hear people, I mean, in talks, you hear people saying that this has to do with this quote, the Red Queen in Lewis Carroll that goes very fast, that say that it's a very slow sort of country, which I think was popularized by Thatcher. I think Thatcher used this. And, but it's, I mean, this is not what you find in Lévy-Leblond paper. Lévy-Leblond paper say that for him, he want to use Lewis Carroll name because it relates to this Mad Tea Party. I think the picture is that all these crazy person, they are all in their very own time. They evolve here, and their time are not talking to each other. It's actually, at least this is what you find in Lévy-Leblond's paper. Okay. Now, of course, once again, null-infinity is conformal geometry because it's the conformal boundary of something. So you do not have a Carrion manifold; you have a conformal one, which just means that this object get weights, they get rescaled. You have a conformal metric on the base now and a weighted vector field. And now, as I already told you on Friday, an essential fact is that the BMS group is just the group of this geometry. Okay, so and the group of automorphism, again, just by the obvious notion of automorphisms. You look for a subgroup of diffeomorphism preserving the structure. Yeah, so that's one way of thinking of the BMS group as automorphism of the boundary. You can also think of it as being asymptotic symmetries in the sense that I will try to explain later on, but they are really the two same notions. Now, here we come to the interesting story, is that if you're thinking, yes?
How much of the BMS group is due to the fact that you are conformal? So what would happen if you look at a metric of the same type? in the simple breakdown and become finite dimensional?
No, it will, you see, that's just this part, that you have conformal transformation of the on the quotient. The line would be the same. I mean, you would still have super translations, because you can just translate along the fiber and there's so infinite dimensional, yes.
So you assume that the lines actually follow nicely the space because you wrote this infinity of S, right?
Yes. Yes, that's what I said. I mean, part of my definition was that the space is just a trivial R bundle over a sphere. Of course, you could weaken that. I mean, most of what I'm going to say is just local statements. You could weaken all of this, but for concreteness, it's good to think that you have a trivial bundle on that. Okay. So yeah, again, if you're thinking in terms of the homogeneous space, so if you're thinking that Minkowski space is some homogeneous space for the Poincare group, I think I convinced you hopefully on Friday that then the boundary also should be an homogeneous spaces for the Poincare group, and this should just be this homogeneous space. Now, clearly, this homogeneous space has a Poincare group action, but there is no preferred Poincare group inside BMS. Okay, it's a fact. So, question is, what are you missing? What do you need to pick one Poincare group inside BMS? What is the extra differential geometrical object that you need to do justice? So, okay, obviously, at this stage, considering the month that we had here, and the discussion I gave on Friday, I think the answer should be clear. What you need is a Cartan geometry model than this. This is clearly the answer that you should have. But this is definitely not what appears in the literature. In the literature, you would have the same type, the following type of answer. So what you should do is look for a BMS expansion. So you take your space-time, you open up your asymptotically flat space-time in local coordinates, and then you realize that there is this object that pops in at first order. So here, H is the boundary metric, and this here, essentially, this the form of the metric tells you that the normal is just du, and there is this object popping up at first order, TAB. It's called the asymptotic shear, and what you find out is that you can define asymptotic symmetries as being the subgroup of diffeomorphism preserving this form. And what you find out is that if you impose that CAB is 0, suppose you can do that. You choose CAB is 0. The subgroup of asymptotic symmetries of diffeomorphism preserving this metric and preserving the condition CAB equals 0 is just the Poincare group. That's the way things are understood. So this CAB, you can think of it as being the asymptotic shear of a null geodesic congruence of line going to null-Infinity. And I should say that in D equal 4, in general, there is no reason why you should be able to choose CAB equals 0. In general, you cannot do this. And essentially, the obstructions are gravitational radiation. I'll come back on this. Okay, so there is this classical question: what do you need to pick one Poincare group inside BMS? There is this classical BMS expansion answer. This is this coefficient. Choose this number, and this does the job for you. There are invariant discussions which are very nicely discussed in Geror and Ashtekar work from the 80s. And I'm going to try to give you, I think, what I think is more compelling presentation in terms of Cartan geometry. I think you will find out that it's very natural. Okay, so just to make it very clear, let's redo this for ADS3, and we'll see that for ADS3 the answer is obvious. Well, I mean, it's already known. So for ADS3, the conform boundary is just a two-dimensional conformal geometry. So conformal geometry in 2 dimensions is trivial. It's just you get a space of null lines, so it's foliated by null line, so it's topologically S1 times S1. Group of automorphisms is just diffeomorphism of circles. So you have diff S1 times this S1. It's infinite dimensional. What again? You could wonder, what do I need to pick PSL2R times PSL2R into this diff S1, diff S1? This is something which is very well known in the literature. What you need is something called Mobius structure. And one way of making sense of this Mobius structure is again by going in local coordinates and doing now Fefferman-Graham expansion. So the BMS expansion was some sort of flat version of Fefferman-Graham. So you run your Fefferman-Graham expansion at second order. There is a free data, and this is just a quadratic differential. This is something which is completely standard in 2-dimensional conformal geometry. And now, once again, you see just the fact that if you look for the subgroup of diffeomorphism stabilizing this, you find diff S1 times diff S1. But now, if you ask that QAB is 0, you'll find out that is just, it will pick up for you some PSL2R times PSL2R. So this is Mobius structure. Yes.
You're looking for the equation at squared of t is equal to 0, right? That's what you need to do.
Yes.
Because this is what singles out the translation inside the super translation.
Yes. So,
And also, for instance, in conformal stuff, you have to look at the Schwarz derivative.
Yes, that's yes. So yeah, indeed. So what could happen? You change coordinates, and you find that under change of coordinate, this object is transformed. Like indeed, this object would transform with the Schwarz derivative. The CAB would transform by f squared equals 0. Indeed.
You're trying to see that coming out of some structure. That's what I'm not completely understanding.
So let me here it is. So in three-dimensional case, in three dimensions, it's you have a very clean Cartan geometry interpretation of all of this, which goes as follows. This is this Mobius structure stories, and I've learned this from Calderon. So what you find out is that in two-dimensional conformal geometry, you always have a tractor bundle in the sense that we discussed this week. It's always there. It's canonical. It's unique. However, the fact that you have this infinite dimensional group is closely related to the fact that there is no unique normal tractor connection. It's not unique. There are many of them. And precisely, the space of normal tractor connection, it forms an affine space, which is isomorphic to the space of quadratic differential. So if you want, that's, I mean, this object is an invariant way of talking about this coordinate discussion just before. Okay, so if you, well, yeah, of course, it's, yes, this is. I mean, you need to choose your BMS coordinates. So you pick one set of BMS coordinates, you write up something, and then you change.
This is in the embedding. In the end, wouldn't you say that F is a well-defined operator on the celestial sphere, or whatever you want to call it? Independently of the coordinates that you're choosing, you don't need to take the conformally flat coordinates.
Yeah, let me say this understand. I mean, CAB equals 0 is not BMS invariant. Like if you change coordinate, you would change. So yes.
About the consequence of keeping it 0 under transformation,
yes.
which is at squared of t equal to 0.
Yes, this is BMS invariant. Yes.
This is BMS invariant for sure.
Yes. But so the way to say it here is that this CAB, this QAB, is a component of an invariant object. This is the connection. What you're looking, but perhaps you see. Okay, okay, here, let me just say this. So the question is, suppose I give you some QAB, suppose I give you some CAB. How do you know that you can actually always change your coordinates and make it to 0? And the answer is, from this picture is clear, is that this object is just a connection. You compute the curvature. The curvature is the obstruction to, you're looking for a system of coordinates where your object is 0. The obstruction for finding such system of coordinates is just the curvature of this connection. So in 2D conformal geometry, what this means, you compute the curvature, it tells you that if the curvature is 0, your quadratic differential should be holomorphic. And you know that when the quadratic differential is holomorphic, indeed, you can just do some holomorphic transformation and put this Q to 0. And then the remaining holomorphic transformation, which are going to preserve this, would be PSL2R times PSL2R. So in gravity, it would be the same. In general, there would be some curvature. That would be gravitational radiation. This would be the obstruction, very clearly, it would be the obstruction to finding a system of coordinates where the CAB is 0. When it's 0, you can find a system of coordinates. And then it picks up Poincare group. Yes, I don't know if you feel this is convincing.
About actually curvature, you already have, because it's like product of two one-dimensional geometries, right? So if the curvature is actually integrability of the splitting, right? Because each one-dimensional geometry has no curvature, right? So just projective structure. It's just projective structure and one-dimensional projective structure are the same.
I think you're right. In this case, yes. I think in this
just coming because the same is simple actually. In this case, not simple.
I think you had the Riemannian picture in mind, where you do need this holomorphic condition. In this Lorentzian signature, somehow the curvature vanishes eventually. Yeah, true. Okay, so exactly that's sort of what I really want to say. That exactly the same picture that, so there is this very canonical picture that is very well known in 2D conformal geometry. Exactly the same is happening at null-Infinity. So in this sense, whatever you think is strange about conformal Carrion geometry is not, because it's exactly the same thing which is happening in two-dimensional conformal geometry. So here are a bunch of facts, is that you can always define a tractor bundle, which I call null tractor bundle, and it's unique. It's just as canonical as in 2D conformal geometry. However, the fact that you have this infinite dimensional group of automorphism means that this tractor connection, again, is not unique. There is a choice in compatible normal tractor connection, and choosing this, well, it's an affine space on something which crucially depends on the dimension. And if you try to run, and I'll discuss this later on, but in dimension bigger or equal to 5, all you have to choose is the zero mode of this asymptotic shear. In dimension 4, this full trace space symmetric tensor is free, and in 3D, then the free parameters are mass and angular momentum aspect. So if you want, also it's another remark. In some sense, this picture it fully unifies the 3D case with the 4-dimensional case. It's always the same picture. You're missing something to choose your group, and this is always a normal tractor connection that you need to pick, and it's either CAB in 4 dimension or this object in 3. Okay, and they are just Cartan connection model on your model, and therefore the curvature is the obstruction to finding a system of coordinates where it's 0. So nothing to guess here, it's just immediate. Okay, so that's sort of the intrinsic picture, but of course you should have in mind that there is a very immediate, there is a close relationship with the ambient tractors of your space-time, as that Rod discussed with us. So this is because you can rephrase the conformal asymptotic simple condition as follows. Now, the conformal metric is equivalent to a Cartan connection, which is valued in the conformal group. This scale, in fact, can be rewritten as being this infinity tractor, and Einstein's equation are just this compatibility equation now, di equals 0. The cosmological constant is I squared. So again, lambda positive is ADS, etc., etc. But this formalism gives you, I'm just going to advertise this again, is a manifestly Weyl-invariant formalism. You had Weyl rescaling here. They are manifest now because everything transforms covariantly and the Weyl rescaling. If you change your, choosing a metric is a trivialization, changing your, rescaling your metric, transform your fields in a linear way. And also what you gain is that there are no divergences anymore. Everything is smooth to null-infinity. Okay, an important remark is that this equation, what it effectively does is that it reduces the holonomy of this connection. You started with a connection which is valued in the conformal group, because now it preserves one direction, it's reducing the holonomy, now the holonomies are valued in the Poincare group. And so how does it fit with the picture that you might have in mind? Fit as follows. So anywhere in the bulk, we have this compensator, but we can fix it. So you can fix this gauge. You have a physical metric. And if you look for what is this Poincare connection, this is just the McDowell-Montsouris connection. So in the bulk, there is no surprise. But now, by this very same reasoning, and as Rod told us, you can just restrict this connection at the boundary. And then you get something which is, and there is no guess again, everything is immediate, and you get this Poincare connection at the boundary, which is of the type I just told you. So the boundary, so you know, one thing is that somehow this trick of going in the conformal group tells you how to induce something, you know, the McDowell-Montsouris connection blows up at the boundary, but going through this trick, you can sort of restrict it at the boundary if you want. So this is a particular case, of course, of this orbit decomposition that we've been discussing during the week. And so, of course, the message here is that asymptotically flat spacetimes, of course, they induce more at the boundaries than just this conformal Carrion geometry. You get a full Cartan geometry. This is how you get it. And again, there is no guess. It's just systematic. It's there. Okay. So yeah, that's once again same summary. You had adapted coordinates. In coordinates, you have the CAB and the Newman-Penrose coefficient. But in fact, they are tractor connection is an invariant way of talking about the CAB, and the Newman-Penrose coefficient, they are just coordinates for this curvature. So in particular, it's immediate now that vanishing of this Newman-Penrose coefficient is just vanishing of the curvature. It tells you that there exists a system of coordinates where the asymptotic shear is 0. So no, once again, I mean, these are known statements in the literature, but here it's transparent why this happened. Okay, so now, so this was like the ambient picture. Let me now go to something, not to discuss how would you sort of derive this in a fully intrinsic way. Suppose you forget about space-time, you don't even know that space-time exists. you just care about conformal Carrion geometry for some reason, and you want to run your try to define some tractors from that. Okay, so again, we start with a conformal Carrion geometry, which is this object, and you have weighted vector field and weighting metric. So my dimension is now n, where n is d-1. And here you have the following fact, is that there exists something which is null tractor bundle, so in an n+2 dimensional vector bundle over null-Infinity. So just like usual tractor, you had 2 extra dimensions. It's canonical in the sense that I'm going to explain, in the sense that you can construct it as being some subset of the second jet bundle of weights. It is equipped with the following things, which comes canonically. You have a degenerate metric. This degenerate metric has rank 1, and there is a nowhere vanishing section, which is preferred, which is this I, which is spanning the degenerate direction. Then, as always, in tractors, you have this preferred null section. Okay, so in this sense, you see it's very similar, very different. They are null tractor, just because the conformal Carrion geometry is null, degenerate. Okay, so how would you derive these objects in a unique way? So let me pick coordinates on the infinity. So YAs, they are coordinates on the 2-sphere. U, they are coordinates along the degenerate direction. Turns out that, and suppose that L is a section of the weight bundle over Scry. Turns out that this operator here actually defines a section of, you compute this, it actually defines a section of the dual bundle. And therefore, this is a well-defined differential operator. It takes a section of the weight bundle, weight 1, to one form. It's always there. So one thing you can do now, you're going to look for the subset of the second order jet bundle, which are formal solution to this differential operator. Okay, and if you look what it does, so you have what do you have? You have derivatives which are du.
Yannick, sorry. Can you go back to the previous slide? Because I'm confused with the dimension. The Carrion manifold is
dimension n.
-1.
So it's, as always, tractors are n+2 dimensional, where n is the dimension of your manifold.
So Carrion manifold is dimension d-1.
Yes, so d is the dimension of the space-time, and n is the dimension of the boundary.
Okay.
And the tractor bundle is n+2 dimension. Yeah, and here is d. Of course, this is really d, so it's not n. So how many derivatives you have? You have du, you have du, dA, you have dA, dB. Okay, so looking for a formal solution of this differential equation, it fixes this part of the second jet bundle. But this last part, dA, dB, is free. Now, one thing you can do is that of course, as always, there's an injection into this solution of the trace-free symmetric tensor. So we are going to consider those which are trace-free symmetric. You inject them into this formal solution, and then you quotient by this trace-free symmetric tensor. So all you're left with really is just, morally speaking, all you're left with is the pure trace part of these derivatives, which is just one number, and then you have the right dimension to be a dual tractor bundle. This exists. This is what you want to call the dual null tractor bundle. Okay. Now, if you want to do tractors, you need splittings for your tractor bundle. Where I am, yes. Just like so, but the difference now, there is going to be crucial difference here because everything is degenerate. So what's going to split your tractor bundle is not anymore a choice of metric. So in usual tractors, you choose one metric in a conformal class and split your tractor bundle. Here, it's more complicated than that, but not too much. What you need to choose is a trivialization of your bundle. So you choose a function u on sigma, which trivializes your bundle. Okay, so it just gives you this r, and in particular, it's such that its derivative in the vertical direction should be non-zero. Now, because n is weighted, what it gives you is a weight, and you can use this weight to trivialize your other field. Yes, you choose a function u and sort of trivialize everything, which is essentially what you do when you work in coordinates in the physics literature. And in particular, now if you take any other trivialization, then you will see that your field transforms like this, where this lambda is now derivative of u hat with respect to n. Okay, so one thing also that, of course, such trivialization does is that it splits your tangent bundle. You already had a vertical direction. Now you have a foliation by u, so it also splits your tangent bundle between tangent direction, between vectors which are horizontal, which I'm going to write with this abstract YA indices, and the vertical direction, and this is going to be the YU part. Okay, so with all of this, you now have a notion of a splitting for null tractors, which goes as follows. You choose one of these U, which is a trivialization of your null-Infinity, and doing this, it gives you splitting isomorphism for your tractors, which is of the following form. So you have, so R, so here I'm also using the metric, there is a scale, so I'm also using this scale to trivialize the weight bundle. So this is why I write them as R, but this is really weight 1, and this is weight -1, right? As you see here, it transforms with lambda, and this one is lambda -1. It looks a lot like your usual tractors, but there is something very, well, the transformation rules are not that as simple as you might expect. This U is this. And the beta, I don't even want to write it because it's quite painful. You have second derivatives on this U. But as always in tractors, the whole point, you don't use this. You need to prove that they exist, that you have the splitting isomorphisms, and then everything is going to be covariant, and you just don't really need to know what exactly these transformational rules are. It doesn't matter that they are complicated. The whole point is that they exist. And this is going to give you, if you want, a covariant way of talking about trivializing your bundle and all these things. Okay. Yes. Okay, and in such splitting, the metric, of course, is just y plus y minus paired. Then YA, we have the conform metric on the base, and this YU is the degenerate direction. And you see it's preserved by this transformation rule, so indeed the degenerate direction is preserved. One interesting thing you can do is you have this preferred null direction, I, so you can quotient by this. Quotient by this I, you take the, so you're just getting rid of this, forgetting about this line, forgetting about this one. What you find out is that you find something which looks a lot like your usual tractors. Indeed, what you can prove is that this quotient bundle is canonically isomorphic to the pullback of the tractor bundle on the quotient. So remember that on the quotient, on the base, we had a conformal geometry. You can pull back this this tractor on the base, and they get canonically identified with this quotient. In some sense, the full null tractor bundle is nearly just taking tractors on the base and pulling them back, but not quite. You have more. I think that's what is interesting, is that slightly more than this. Yes.
Each time, what are the dimensions?
Dimensions, yes. So YA is a tangent vector to the sphere, so it's, if you want, 3-dimensional. Then this is 3 and 4. So this would be your tractor bundle of a 2-dimensional conform manifold. Right? 2 plus 2. But then YU is that vector in the vertical direction. So these are 3 vectors on your infinity, and you have 2 dimension. X5. Okay, so how do you derive these splitting isomorphisms? Essentially, what you need to do is you need to find out the good Thomas operator that does the job. And it exists. So I'm not going to spend too much time on this, but just to review, there is something like a Thomas operator. You take a scale. So what's interesting is that it's not any scale. It already should satisfy some differential condition. And here it's really where the null feature comes in. And then any such scale can be uniquely lifted into a null tractor. It sort of gives you the isomorphisms. So in the sense that it tells you that you can identify this second order jet bundle with your split it by using this Thomas operator. Okay, yeah, and again, if we can think of null tractors, another picture is that they are associated bundle for this P, which was the stabilizer in the homogeneous model. Now, let me come to normal tractor connections. Now we're constructing these null tractors in a canonical way. And I should say it's as good as the usual tractor. It's as canonical and as unique as the ordinary one. And now you want to construct tractors on them and look connections on them and look for a normality condition. The first thing is how do these things transform? Well, remember, we know that we choose one realization, we have a null tractor. If you choose another one, you add. Then these tractors, they transform by some linear transformation. So connection, you do the same. You have some trivialization, you have some trivialized potential. You have obvious usual gauge transformation on your potential. There is no case. This is how things should transform. Now, if you require that your connection is compatible with the degenerate metric and this preferred null tractor, it's automatically valued in the early algebra of the quantile group, and you can split it in this splitting. You can write it like this, where there are all three coordinates. One first thing you should require is that it's compatible with the Carrion geometry. Right? You start with some informal Carrion geometry, as always, there should be some sort of compatibility condition, which is freezing these parts. And now you can impose normality conditions. So first one is obvious. This is the same as in conformal Cartan geometry. You ask that the torsion is 0. And then you need to impose something on this part of the connection. And then it's not your usual Ricci flat condition, but it will be too weak. If you just impose this, you will not. Basically, you will realize that there are some other equations that you can write that can constrain the connection further. So here are constraints which are the best in the sense that any other constraint would be differential and not algebraic. So we have this degenerate vector field, so we can plug it in the 2 form, and it should be 0. So it's basic if you want this 2 form. And then you trace over now the form indices in D, and this only makes sense because this is
With this one, you kind of guess. I mean, they are very natural. I'm perfectly happy. But just to make you.
So I mean, yes, in the sense that there are not much you can require, which is going to be invariant, right? So there are not many conditions which make sense in the sense which are covariant into gauge transformation.
So it's
not the way. So I mean, that's the first one. Yes, you guess them because there are not many that are invariant. Then you can sort of convince that they are the good one by checking that this condition they pops out by imposing. If you try to construct this connection by taking the bulk tractor connection, you're trying to induce it at the boundary. You do this and you realize that Einstein's equation force this. Then you realize that indeed they are the good ones. But it's actually more complicated to do this than just guessing and finding the correct one. Yes.
And which algebraically is it still in conformal algebra?
Yeah, in Poincare algebra.
Because it's degenerate direction.
Because it's degenerate direction. So I mean, again, the idea is that you should think of the Poincare group at null-Infinity as being a conformal Carrion group. That's really the way you should. Okay, and then you run through this. Now you run through the computation and you figure out what is free and what is not. And then you realize that, again, depending on the dimension, something very different happened. And essentially, yeah, you impose distortion freeness. It solves the connection as a function of H, and psi and these C's, they are symmetric. You impose this null condition, which constrains the trace-free part of psi, which is just CAB dot, where dots are derivative in the vertical direction. Here you find this n-2. So this equation is trying to constrain the trace of psi, but in dimension 2 it cannot, and this will be the mass. This would be your mass angular aspect in n equal in n equal 2. But in general, it's constrained, and this has to be this is the constraint. And then you impose this trace condition, and here in general, the derivative of your shear would be the trace-free Ricci. But again, in 3 dimensions, it's not, and it becomes completely free. And this psi, same thing, this would be the angular momentum aspect in n equal 2 dimension, otherwise it's something free. Again, here it's like just a computation, and you see what sort of fields parameterize this connection. Okay, let me come back to the, yeah, I mean, is there any question at this stage on this? Yes? Yes.
Where does one see that the difference between zero mode and
So here you see, in general, there would be dimension bigger than 3. The derivative of CAD mu is constrained as being this object. But in n equals 3 is absorbed. I mean, this is anything.
Well, one question I have, so I can understand why you don't like CAB in a sense, because it's part of the metric and it's the coordinates
Yes.
of the better object. What about the first order version of that? If you do it in Newman-Penrose formalism, right? I mean, then the CAB you already have sigma, which is in fact coordinate independent because it's a scale, right?
Oh, it's coordinate dependent. It depends on the sort of frame. So
It depends on the choice of the local Lorentz, but no longer on the choice of coordinates,
Yes.
right?
Yes.
Okay, that was my question. So is because then you want to look how this guy transforms. It's also at squared of t, right? Finishing of that. So your object is also invariant under local Lorentz.
This object makes sense without using coordinates. It's fully invariant object.
Sigma. So you are saying sigma, the asymptotic part of the shear, needs
It's
coordinates.
one of the coordinates of this object. So I mean, you see, it's like you're saying, it's really we take Young-Mills, but say, I'm telling you there is an object which is a principal connection which makes sense. And then in any set of coordinates, this is some potential that transform in this and this way. But this asymptotic shear, either in BMS coordinates is the CAB or in Newman-Penrose is the sigma. They are just objects that make sense. You need to make some choice, right? You need to choose state frame or whatever. This exists without any choices. This is just there. This is an invariant object. And then you can pick coordinates and compare with whatever you want to compare. Yes. And again, it's an invariant object, but it's even more than this, is that you know that curvature controls the behavior of this object. Again, yeah, perhaps I should say this. Now you can just take this with this, you replace by the explicit expression, you compute the curvature, and you find the Newman-Penrose coefficient. You don't even know about space-time, but this computation, it would compute this for you without even you knowing about Newman-Penrose coefficient. Okay. Now let's again relate this to ambient tractors, and perhaps that would be even better answer to the question. So I showed you this picture. Of course, it was quite imprecise. Exactly what do you mean you induce the connection? What exactly? We need to work a bit more. So now we have. I told you that there is a good definition. We have a conformal Carrion geometry at the boundary. There is an invariant geometry of tractors living on this type of conformal degenerate geometry. This is this null tractor bundle. We also have tractors in the ambient space. And now you need to identify these tractors in the bulk with your tractor at the boundary. So in the usual things, you can do this. Rod explained us how to do it. In the null case, you can also do it, but it's slightly more painful. But again, you can prove that the null tractor bundle at scry is canonically identified with I perp, so you take the tractors at the boundary, you have this preferred tractor I, you look for the orthogonal space to this, and you can prove that these are canonically identified. There's no choices, they are the same. And then the normal tractor connection in your space-time, it induces on this bundle, and therefore on this bundle, normal tractor connection. Here, if you want to know the result, because indeed you need to check that Einstein's equation, this is indeed Einstein's equation that makes sure that this induced connection is normal. In general, it will not be normal, but Einstein's equation at leading order, you can precisely check at which order, impose that this induced connection is normal. And then here's, I think, how do you do this? How do you identify? Here's the important, I think, the key realization is that choosing a trivialization on scry, as I told you, it defines the splitting for this tractor bundle. It's just there, it splits your tractor bundle. At the very same time, you can prove that it defines a preferred scale in a neighborhood of scry. There is a procedure which is actually quite closely tied up to BMS coordinate that essentially does this. You choose U at the boundary and it gives you a unique scale in the bulk. Now you have a preferred scale, so you can trivialize your tractor bundle. Now with the very same object U, this trivialization, you split your tractors and you split your bulk tractor bundle, Now you can try to match them and check that everything works out. It does. I mean, you can make sense of this. And perhaps last point is that choosing this U is also the same as choosing null geodesic congruence, and then you can define the asymptotic shear of this null geodesic congruence. And you see that it's, this U is coordinates. So all this part, if you want, is coordinate free, fully. And here at some point I make some choice U, which trivialize everything at the same time, and now I can compare. I can compare the asymptotic shear of my null geodesic congruence with some coordinates arising in this splitting isomorphism. Yes, so indeed, now once you have this, it makes sense of comparing things. You trivialize your tractor bundle. There is some coefficient which is CAB. You also choose a null geodesic congruence, and you look at the asymptotic shear of this null geodesic congruence, and now you can just check that they are the same things. So indeed, this freedom CAB is just to coordinate things parameterizing this boundary null tractor connection. Any question on this? I think that's really key to make sense of what. Yes.
I'm a bit confused. This null geodesic congruence, where does it live? This null geodesic congruence?
It's in the space-time. Right? So
you're viewing this as a boundary of your Carrion geometry is a boundary of this system.
Yes. Yes.
And then the ambient.
Ambient tractors, they are tractors for your space-time.
This is ambient for space-time.
Yeah, that's what I'm trying. Yeah, that's what I mean by ambient. Sorry. Yes. Yes. Yeah. So perhaps you said bulk. Perhaps is better the terminology. Indeed. So you have these tractors in the bulk, and you identify them. There is a sub-bundle of these bulk tractors which get identified with your boundary tractors. And then there is choosing this U, you can choose coordinates, you can trivialize everything at the same time. Then you can compare and check that everything makes sense. Okay, so null geodesic congruence, they are of course choices, and they split your tractors. Now this was very quick. Okay, so what I tried to tell you that there's a well-defined notion of tractor bundle on a conformal Carrion geometry. Exists, you can make sense of it, just like in 2D conformal geometry, it's there. However, the fact that we have asymptotic symmetries is related to the fact that if you try to cook up a notion of normal tractor connection on this, it doesn't exist. It's not unique. Well, it exists, but you have many. It's not unique. Just like in 2D conformal geometry, we have a whole family of this normal connection. Here we have a whole family of this Cartan geometry. Now, anytime if you're thinking of this conformal Carrion geometry as being at the boundary of something, at your boundary of your space-time, then you can induce a preferred connection from the bulk. So it picks one for you. So in all dimensions, but d equal 4, this is slightly boring because everything is flat. So Einstein's equations are going to impose that this connection is flat, and therefore all you have is a gravity vacuum. Meaning what you have is a map from Scry to your model, because that's what Cartan connections are there for. When they are flat, they give you a map to your model, and in particular, they choose some Poincare group inside BMS. But in dimension 4, there is something more interesting happening, is that this boundary tractor curvature, actually it invariantly encodes a presence of gravitational radiation. And by this Cartan results, it means that gravitational radiation, in this very precise sense, this is the obstruction to finding such an isomorphism. Gravitational radiation, they are the obstructions to identifying null-Infinity with your model. And there is, in fact, last thing which I actually, unfortunately, don't really have time to discuss is that there is a sense in which you can precisely says that gravitational radiation, so presence of curvature, is going to give you a transition between gravity vector. You can actually, so this would be memory effect in this geometrical perspective. Okay. And so now, what's next? What can you do with all of this? So one thing is that there is something slightly immediate, is that you can just write a Chern-Simon functional for this connection. Connection in 3 dimensions, you look for the Chern-Simon functional. Of course, the field equations are going to be flatness, and we know that the flatness means absence of gravitational radiation. So it would give some sort of effective action for this boundary degrees of freedom. And this has been discussed in this work. And then perhaps more interestingly, the whole philosophy that we've heard this week is that the whole point of tractors is that they are meant to proliferate invariants, produce things that you would not have guessed. So I think the pressing question is, can we use all this machinery to produce new invariants for asymptotically flat spacetime? And of course, this will be physical, just as because asymptotically flat spacetime a very clean physical interpretation. The last point is more conceptual, but I think just as important, is that the fact that you can now rephrase the whole geometry of null-Infinity as being this Cartan geometry, it immediately suggests generalization that it immediately suggests them. One thing would be to enlarge this connection into to the super Poincare group. In some sense, all this can give you is some sort of notion of super conformal Carrion gravity, lots of words. There's some sort of gravity theory living at null-Infinity with this super DMS hidden in there. Other obvious generalization would be to look for higher spins, as we heard during this month, that there is this intuition that in some sense higher spin can be understood as being some sort of Cartan geometry for higher spin symmetry. That's another direction. So yeah, it's all very natural at this stage. Okay, and I think that's all. I thank you for your attention.
Thank you. Are there any questions? Come back.
Okay, so it's partly a remark and partly because you were saying also during Roth's lecture that you were showing that something similar happens if null. Yeah, but the difference between the two settings is here you impose that in the interior you are Einstein. Yeah. So you impose that the scale tractor is parallel. Whereas in Roth's talks, these assumptions were often weakened quite a lot. Sure. And then dealing with the null case is much more difficult. This is why he was hesitant to say it's very similar if you are null. Because if it's non-zero, then it suffices to say that the limit is non-zero plus the boundary to get some fairly strong statements. And in the null case, this is not. There's no analog to that. Mm-hmm. If you assume that it's parallel in the interior, then it's similar, closely parallel.
Yes, that's why I was really referring to the second lecture. It was really dealing with this conformal.
No, this was more general. Yes. It was not Einstein in the interior. It was just conformally compact, usually. Yeah. And the assumptions were just that scalar curvature has a non-zero limit. Mm-hmm. Okay. But anyway, it's just to make sure that there is no confusion. Yeah, no, sure.
Why gravitational radiation is different in higher dimensions?
Yeah. So I mean, see, one way of thinking of this construction is that another way of phrasing is that this boundary, this induced fractal connection, what it captures is the very first jet of the inside asymptotically flat spacetime. But in higher dimension, gravitational radiation, they are not at this order. They are subleading in the expansion. So this is why you're not capturing them in this picture. Because this connection here, just look at just see the first order.
So, again, page 31, when you were saying how you end up with a null geodesic congruence, and are you saying that this CAB that you put here, maybe I understood incorrectly, that you're making it shear free, or did you relate that normalization to being shear free or no? No. So what I'm saying is that anytime you pick a foliation U out of your conform boundary, defines for you uniquely a null geodesic congruence in your spacetime. I think which now what people call CAB is the asymptotic shear of this null geodesic congruence. Okay. That's what I'm saying. And then I'm saying if you now open up your tractor connection
the free parameter is precisely this asymptotic shear of the null-geodesic congruence. Now, you might ask, when can I choose a null-geodesic congruence which have zero asymptotic shear? And here the answer here is, because this means when can I choose a visualization U so that my Cartan connection is flat? And the answer is you can do that if and only if the curvature is zero. So if you want, curvature of the fractal connection is the obstruction to finding this asymptotically shear-free null-geodesic congruence. Okay? But and
So this is curvature of the tractor connection where? For your boundary or?
They are related. They are very closely related.
But they have different curvature.
I mean, just you take the curvature of your bulk tractor connection, then you restrict it at the boundary. It turns out that this is just the curvature.
That's zero.
This is zero. Yes. This is your obstruction. It's something that just lives at the boundary because it's asymptotic shear. This is asymptotic. So it's just something you see. And in the bulk, yeah, okay. So in the bulk, the tractor curvature is essentially the vitance. So actually, really, this is a Weig tensor, but evaluated. Yes, yeah, Weig tensor control gravitational relation. It's not a big node way of saying it. So indeed, yeah, it's not the full Weig tensor. You need to contract this with your normal. Weig tensor contracted with the normal is this curvature, and this is what people call gravitational relation.
And just to explore, and we agree this geodesic congruence, precisely when if it were working, would allow you to reconstruct points in the interior. Is it correct? That retrospectively, a point in the bulk, if you look at the light, that is
it's a slightly different story. Yeah, so you're asking if you're asking the other way around. You know, if I take a point in the space-time, I can shoot the null cone from this point. I will get a cut of null-infinity. And in general, this cut would not be any cut of null-infinity. It would satisfy the good cut equation. One thing you can prove is that essentially such cuts, they are closely related with parallel transported tractors at null-infinity. So essentially, you can see that parallel transported tractors at null-infinity, they are one-to-one correspondent with these good cuts. This cut comes from the space-time. Yes.
You make this connection between asymptotic symmetry and non-uniqueness of the connection. You mean enhanced asymptotic symmetries, I guess, the ones where the asymptotic symmetries are the same than the exact isometries of the background. It should correspond to then the unique ones.
That's what I mean, yes.
That's what you mean?
Well, it's bigger than what you
expect. Bigger than what you expect from the background.
Yes, yes. You see, here you can say like you expect to have a unique connection, but it's not. And
you focused a lot on flatness of this boundary connection. Mm-hmm. What happens if it's not flat? Can you still choose the additional data to get a unique normal tractor connection, or is there nothing like that?
I'm not using the flatness in this derivation of the normal. I'm not using flatness. The normality, the normality conditions, they are independent of the question of whether or not the.
Yeah. But then you say it's not unique.
Yes.
And in flat cases, you find something unique.
In flat cases, you get differential. It gives you differential constraints on this. You see, it's like two-dimensional conformal geometry. You get this quadratic differential.
But two-dimensional conformal geometry has a non-flat version. Not everything flat.
Yeah, it's the same. Exactly here the same. You have a non-flat version. In exactly the same. So in two-dimensional, you have non-holomorphic quadratic differential. Here we have this CAD can be very long. The curvature would be some differential constraints on this CAD. Completely parallel to 2D conformal. So when you have zero curvature, you have this differential equation on this object. It just means that there exists a system coordinates where these guys can be taken to the zero. So we can discuss it.
one more question. This differential thing, is this the electric condition like x squared of sigma or something equal to 0?
It's psi4 equals 0, psi3 equals 0, and imaginary part of psi2 equals 0.
But this is for the while part of for the projected while of the curvature, right?
Yes.
This is the equation.
This is the equation. This is the curvature.
And then your Einstein equations relate all of that, of course, right? To things are not independent. I mean, you have imposed Einstein's equation in the back, right?
Einstein's equation tells you that this connection is normal. In general, it could be very complicated. This normality equation that I showed, they are in this picture, they are imposed by Einstein's equation in the book. If you want, you can derive them in this sense from this perspective.
I guess I was asking if your differential equation had something to do with the good cut equation, but somehow
Good cut equations are, so a good cut would be essentially one-to-one with certain types of weights that exist at null-infinity, and weights which give you parallel factors which are parallel transported would be one-to-one corresponding to good cuts. What I mean, like a cut would be like some tractors living at null-infinity. This tractor is coherently constant if and only if the cut is good. At good cuts, there are equations on something, and this something is a choice of cut. and in this picture, this something are tractors. And the connection tells you how to make sense of this. But to make sense of the good cut equation, there is sigma 0. So we need to know what is sigma 0. That's what I'm saying.
So that's why for you, that's not a good equation. A good cut equation. I'm joking.
It's good. It's a good equation for something. Yes.